Hi everyone. My name is Roshan. Today I'll be talking about text analysis. So treating text as data. We'll talk about pre-processing as well as topic modeling and sentiment analysis. Let me share my screen. So let's start a little bit about me. I'm currently a PhD candidate at GW. I'm actually about to graduate this year. Defended my dissertation just less than a month ago, and I'm transitioning to be a postdoc at the Institute for Data, Democracy, and Politics here at GW as well. In terms of computational social science, I'm interested in text analysis, NLP, increasingly LLMs, as well as topic modeling and sentiment analysis. But I'm also interested in causal inference and survey experiments. So if anyone is interested in those topics too, let's connect. In terms of research interests, I'm broadly interested in post-Soviet, Central Asia, and Eastern Europe. In terms of topics, I'm interested in political communication, so anything having to do with media, misinformation, propaganda, as well as political psychology, specifically the role of emotions and how emotions impact sort of the way we process information and the way we perceive incoming information. In terms of my research, I was looking at strategic narratives surrounding the war on Ukraine, specifically Russian and Western media narratives surrounding it. This is specifically relevant for this lecture because I will be giving examples of what I was doing here. All right. So in terms of today's agenda, we'll have three sections. The first one is, so the first one is just foundational, text as data and pre-processing. The second one is topic modeling, and the third one is sentiment analysis. Here I'll have to note that each of those topics can be a lecture on its own, and we will have sort of a broad overview here, and I'll try to introduce you to some concepts, but obviously if you want to go deeper into them, you can research more. I'll point you to some resources as well. So let's begin with the foundation, right? The why is text as data important? Well, mostly because text is everywhere right now. The problem with that is that prior to sort of computational revolution, we treated text as sort of those artifacts that we need to engage with qualitatively and interpret individually. And while this is still true, now luckily we are able to analyze data in large amounts, especially with data being produced daily from social media, from news, from all other sorts of entities. We can analyze that more systematically, right? The problem, however, is that a lot of text is unstructured. So computers don't really understand it. And we need to sort of get this unstructured data and turn it into something that computers can understand. So I'm going to try to cover some of it right now. So this is one of the resources that I keep coming back, this textbook called Text as Data. It was written by political scientists, really important book if you want to understand the application of text in social sciences. It's foundational. Obviously, it was written before sort of the widespread use of LLMs, so take that with a grain of salt, but either way, this is an important text for you to read if you want to do text as data in the future. So what is text as data? The core idea is that language often reveals what people think and feel and care about. And those language patterns can aggregate into an important information that we as social scientists can analyze. So text as data just means that we can take those linguistic patterns and sort of convert them into numbers that we and computers can analyze. It's also important. It became important because a lot of the information that we have now is just too much text for humans to sort of analyze individually. So, for example, in my dissertation, in my research, I had more than 100,000 articles, which if I read them by myself separately would take me forever. It doesn't mean that I didn't engage with them qualitatively. Here, I want to emphasize that just because we use certain quantitative techniques, computational techniques, doesn't mean that you as a researcher should not be familiar with your text or with the domain knowledge, but it definitely simplifies a lot of things, and we're able to look at things more systematically, right? Sort of at a larger level. So computers basically lower the cost of this systematic analysis. And the applications of text as data is in many industries. It's obviously in academia and political science and economics, but it is also often used in commercial sphere. So in terms of advertising or sentiment analysis or opinion mining, all of this are increasingly relevant. Also, feel free to interrupt me if you have any questions. I'll throughout the lecture, or if you don't understand something, I'm happy to pause if necessary. So as I've mentioned, in a lot of data comes to us in unstructured ways. So imagine you're reading a news website and you see a lot of words, and for us, those words actually mean something. However, for computers, it doesn't really mean anything because the way computers read and analyze the data is through matrices, right? So the fundamental task of preprocessing or preparing our data for computational analysis is turning it from something unstructured to something that computers can analyze. So this is an example of it, right? Like a lot of text that we observe today comes in just in a block that we understand, but computers don't. What we want to turn and what we want to achieve is this structured data with rows and columns. Another note here is why text can be hard for computers, especially before sort of the large language models and word embeddings that can sort of understand the context of a sentence. A lot of things for computers are sort of not really understandable in terms of irony. For example, here, thanks Obama can mean both praise and sarcasm, and it's a lot of times it's not clear. Some of the language is very subtle. A lot of the traditional sort of machine learning models back in the day also didn't understand the context, didn't understand what word order. So what was important is frequencies, and sentences like peace no more war and war no more peace would mean the same thing for an algorithm in that way. Additionally, with different languages come different pre-processing decisions. Russian, for example, use Cyrillics, and a lot of lectures out there on text analysis use English as an example, but Russian, because of its syntaxes, would have a different, like a little bit different of preprocessing steps, as well as packages that we use, right? Um, Additionally, a lot of language is informal. So some things that come up today, some of the jargons, some of them would be uninterpretable for a computer, especially if it's a dictionary-based approach that somebody would take. Now, when we analyze text, we usually use one of those two strategies. The first one is supervised learning, means that you train a model on labeled data. So you have documents that you or somebody else has manually coded with labels. And let's say this article is about the war, this article is about economics, this article is about diplomacy. So you feed those labeled examples to an algorithm, and then algorithm learns this pattern and applies it to the rest of the set. And it definitely saves a lot of time for human coders, because human coders are A, expensive, B, it's just very attention and sort of effort intensive. So in that sense, it simplifies the labeling processing by a lot. Then the second approach is unsupervised learning. It just means that you let the computer discover patterns on its own. You don't provide labels. You just basically say, here are the documents, tell me what you find. And then the computer finds groups or clusters or patterns without guidance. The sort of downside of it is that it sort of acts as a black box. You don't really understand how computer came up with certain clusters or with certain groups. But the advantage is scalability, that you can do it with, like in my case, with more than 120K articles, that if I did it by myself would not be really feasible. Here's the 5-step pipeline that we would follow. Step 1 is obviously acquiring text. You need a machine readable document. Step 2 is building a corpus and tokenizing it. Step 3 is preprocessing. Step 4, building something called document feature matrix. Step 5 is analyzing. So each of those steps basically involves certain decisions for researchers, and those decisions are important because the decisions that you make here will end up trickling down the pipeline. So the end of your analysis and even what you discover as result, honestly, can depend on the way you pre-process a lot. So every step here need to be done with sort of care. I think we have. Okay. In terms of text acquisition, so that's step 1, right? Computational text analysis requires machine readable text. I think in one of the previous lectures, you were taught how to extract text from PDF, and extracting text from PDF is usually really hard and error prone, and it can scramble formatting. So JSON or plain text is much easier. HTML for websites is also manageable. CSV files as well. It's especially for Russian, I would recommend encoding it in UTF-8. And you would also need to have metadata if you want to analyze certain sort of covariates or metadata that comes attached with the text. In terms of popular sources, there is LexisNexis, Comparative Manifesto Project, Foreign Broadcast Information Service. If you're interested in media, especially, you can also go directly to websites and scrub either through API or just web scrape. The only problem is that there are like legal and ethical dimensions to it as well. Some sites have sort of terms of service that prohibits scraping. Some data is proprietary, so you'll need to be careful and you'll need to check before engaging with web scraping. Another thing is to consider the bias. So when you acquire certain text and you try to compare them, you need to understand your sampling method and how your sampling method can lead to bias. So the next step is building a corpus. A corpus is once you sort of collect your raw documents, you need to organize them into this collection of text, usually in a very structured format. It's not just a folder of files. It's basically amenable to systematic analysis, and it consists of documents, sort of your elements within the corpus. In my case, those were articles. The next one is sort of under the documents, we have segments, which are the elements within a document, which can be paragraphs or sentences, and then tokens. Tokens are usually words, but it's the smallest unit of text you're analyzing. It is usually a word, but you can also include 2 words, 3 words, depending on your needs and on your research questions. This is what usually a corpus would look like. So each document is a row here, and this is from my data. Here we have articles from BBC. Each document is a row, and then for columns, we have one for text, and the rest is for metadata. So here we have date published, headline, text itself, tags, document ID. Document ID is an important step as well, so you can track each document. We also have here narrative, what kind of narrative it is, source, BBC, and days. Days here means just days to the start of full-scale invasion. Okay, so after we have created the corpus, we go to preprocessing. Here, the main idea is sort of to sort of convert the text into numerical representation, so into a matrix that computers can understand and into something that computers can systematically analyze. So the goal here is to convert our corpus to something called document feature matrix or document terms matrix, where each row is a document again, but each column is a unique word, and cell represents the count, so how many times we see a specific word. The problem here is that a lot of text has information that might be meaningless to us. That includes capitalization, punctuation, numbers. If you scrape data from social media, it can be emojis, a lot of slangs, some dates, and depending on sort of the question you're asking, you might want to sort of get rid of some of those features. The problem here is that, for example, if we get rid of capitalization, we, for example, have another question where Turkey as a country and Turkey as a bird would mean the same thing for a computer. So again, have to be careful and have to know your data as well. This is what the document term matrix or document feature matrix usually looks like. It's a matrix that summarizes the frequency of words across documents. So, and here is the number of documents. That's these are our rows, and P is the number of features. Features are just words or terms or tokens, if you want to say so. And then X is sort of X or DFM or DTM, if you want to refer to it as that. It's just the main input for a lot of text analysis. So this is the final form that we want to come to after pre-processing. And here, what it looked like in my case, as you can see, here the picture on the left is what my corpus looked like, and here the picture on the left is DFM, where we see documents or articles displayed on as rows, and we see features or words as columns. And the count is a cell. So for example, this means that in this particular article, the word planeta was saw it 3 times. This is another example. I wanted to show you basically this assumption of a bag of words. Bag of words just means that we're treating the order of words as irrelevant. We only care about the frequencies. So here, Россия новые санкции против западных банков would end up as just count frequencies in DFM. It's definitely a simplification, but it works well for topic modeling and sentiment analysis. So in terms of pre-processing, the way we convert our corpus to DFM usually consists of 7 most common pre-processing decisions, and we'll sort of briefly cover all of them. The first one is punctuation. Oftentimes punctuation is sort of irrelevant and we try to get rid of it. But in some cases, punctuation, depending again on your question, punctuations might be relevant, especially when it comes to analysis of like social media. That would matter, right? So again, a lot depends on your research question, but generally we usually tend to get rid of it. The second one is numbers. Numbers can be relevant, but also can be not relevant. For example, in the case of if we talk about the full-scale invasion, maybe you care about the numbers because you want to track number of casualties, or maybe you want to track the number of refugees. So in that case, maybe you would want to leave the numbers, but often we also get rid of them. Then the next pre-processing decision is lowercasing. It just means that whether the word is capitalized or not capitalized doesn't matter. So usually we just lowercase all terms. Okay. Another important pre-processing step is lemmatization or stemming, and depending on your case, you can either do both for for English, in English, we usually just do stemming. So you cut the end of the words to just have the root of the words, right? But in Russian, we usually go with lemmatization. So that just turning all of the words into a base form. And I use personally PyMyStem3 in Python to turn um, all of the articles I had, all of the words in Russian into the base form. Um, in terms of Russian morphology, that's an important part. Why we need to do that? It's because in Russian we have 6 cases, right? And without the lemmatization, we would have 6 different features in our DFM. But what preprocessing allows us to do is sort of collapse it to just one word. Okay, and then some other final preprocessing steps are stop words and infrequent terms that we also usually eliminate. In terms of stop words, it obviously depends on the language that you use. A lot of packages come with Quantita in R comes with stop words for Russian, for example, but you can also add your own dictionary. So some words might be domain specific. In my case, because I analyzed news articles, I got rid of a lot of words that said news or correspondent or television. So it all depends on your domain as well. Okay. In terms of infrequent terms, some terms are too infrequent or don't matter at all. So it might be worth to just sort of cut 25% of the terms that are really infrequent because maybe they're just meaningless. So that preprocessing decision would allow to, eliminate a lot of the words that you don't need and sort of make the whole process less computationally expensive. Um, another step is multi-word expressions, sort of what tokens do we want to have? Usually we analyze them through unigrams, so each token is just one word. But that's what becomes difficult here is that in different contexts, those words can have different meanings. So, for example, security might have different implications and different meanings in when it comes to social security or national security or security deposit. And so here we might want to include n-grams. So n-grams is basically every contiguous sequence of words. So here, my cool cat Allison would be my cool cat Allison. You can also do it through collocation statistics, so grouping together words that appear together unusually often in a statistical sense. For example, New York probably would appear pretty often together. You can also group them through linguistic phrases in terms of semantic units, so you can always group them as adjective plus noun. But in most cases, people just use unigrams anyways. But again, depending on your research question and depending on your data, you might want to use bigrams or trigrams or any other grams. Second. So after we discovered all of those decisions that we make, what happens is that we might end up with completely different DFMs, completely different final sort of data frames or data structures that might lead us to different results. So it's important to sort of be transparent about it and document every step. And if you report it in your paper, let's say, you should report it and be transparent and just for application purposes, um, show what you did. But also this might and result in different um, sort of in different downstream consequences. And here, Matthew Denny and Arthur Sperling, they came up with pretext package in R that lets you understand how your pre-processing decision can sort of trickle down the line. What it essentially does is it calculates something they call pretext score, and it sort of regresses them on different decisions that you take. Here, as you can see, you can have a graph that looks like this. So in this particular case, you can see that using engrams and punctuation actually did lead to different results. Here it doesn't mean that, here the main sort of concern here is the sensitivity. Are your results sensitive to the way you pre-process information? And you should do it usually before your analysis, so you're very transparent with your readers. Here I just want to emphasize some challenges with Russian language. Again, because of its rich morphology, we need to be super careful about it. With English, it's usually much simpler, right? There are some verbal aspects and prefixes, imperfect, perfect pairs, and those prefixes can change the meaning of the word as well, right? In terms of stop words, again, Russian has a large list of stop words, and you can use the one in Quantita. I'm sure there are other packages that maybe Yandex has developed as well. If you want to look at that. In my case, I also, for stop words, I eliminated a lot of domain-specific terms. I removed Russia and Ukraine to focus on the framing itself of the war. And then, as I've mentioned before, I created a custom dictionary that sort of removed stop words like, or words that were too frequent, like news, correspondent, etc. In terms of my data set, it, as I mentioned, included 125K documents. It came from 7 media sources, and the period that I wanted to cover was just 24 months. So since January 2022 to December 2024. What I wanted to see is how sort of both Russian state affiliated and Western state affiliated media portrayed the war on Ukraine. Here, I had 7 sources, 3 from on the Russian side and 3 on the Western side. The way I scraped them depended on the source. For some of them, I was able to scrape them directly through the website using Beautiful Soup and Selenium. In some cases, I had to download them from the databases and then scrape them from specific documents afterwards. But that's sort of the overview. And that's this graph shows the pattern of articles over time. as you can see here, sort of it all peaked at the beginning of the war, but specifically, obviously, RT produced many more articles than other sources did. I'm gonna pause here for questions. Does anyone have any questions? Are their model contexts reusable better with more cases, or are they used only on the per cases? Um, those models can be used on, I would say, per case basis. Um, I'm not sure what you mean here, but in general, those are applicable throughout, um, on any case or on any domain. It's just, if you mean in terms of the document, um, it's just you can use it with any document. It's just it becomes more computationally expensive as you increase the number of documents. So your like laptop or your machine can crash very fast. Well, if there are no other questions so far, um, okay, let's move on to topic modeling. So topic modeling is one of the most popular tools that a lot of social scientists and also people in humanities work with. And it helps to discover sort of those hidden or latent structures in a collection of documents. So it assumes that documents are mixtures of different topics, and topics are a distribution of words. So topic modeling basically allows us to discover what documents talk about. Um, so essentially what happens is that um, topics here broadly just mean clusters of co-occurring words in a large corpus. So if 2 words or 3 words or 4 words tend to occur together in within a specific article, within a specific document, then those are more likely to constitute a specific topic. Here, it's topic modeling tends to be unsupervised, so you don't need to label any data. You let the computer decide what those common patterns are and what common sort of concurrent words are, and then you need to label the topics post hoc. And that's why sort of domain knowledge and knowing your documents is very, very important, because you won't able to assign a specific topic without knowing what your documents are about, at least some of them. But it's very scalable. It's far beyond what human coders can do. So in what cases do we want to use topic modeling? We usually use it when we want to understand what is the specific large corpus is about. If you sort of want to understand thematic variation within this corpus without manually reading everything, topic modeling is a way to go. If you also want to see how topics evolve over time or how they different across sources, topic modeling would be great for that as well. Topic modeling is not great for something if you want to, for things like labeling data. For that, we need to use supervised approach, and I'm not covering it here. And also, I wouldn't use it on a data that's just a very small corpus. So let's say you have 500 documents. I wouldn't use it there because it's just not a lot of documents, and it can lead to a lot of probably hallucination, and you can just read them honestly by yourself at that point. Okay. So the first topic model I want to cover is LDA. LDA is sort of the workhorse of topic modeling. It's not as used anymore, but it's still worth knowing about it because it was so popular and what started the whole topic modeling um, subdiscipline. It was introduced back in 2003, and it serves as sort of a base for other topic modeling models that we will cover. It's powerful because it can scale to large corpora and it's very interpretable. You basically will need to select the number of key topics that you want the model to discover, and then the algorithm will sort of pick a word in each document and will get it assigned to one of those key topics. Eventually, the model converges, and you see what words occur together, what words what those topics are. Obviously, it will give you the words, but not the topic itself. And here you'll need to sort of there's definitely a researcher degree of freedoms, and results will vary a lot on choice of case, so of choice of number of topics and preprocessing decisions, and you will need to document that too. Um, okay, so the LDA sort of assumes that documents are generated in a specific way, that there is this, let's say, in every document has a mixture of different topics. Let's say a news article, it can be 60% military, 30% diplomacy, and 10% economy. And then for each word in the document, it sort of draws a topic, draw a topic assignment from that topic distribution, right? So the first word comes from topic military, the second word from topic diplomacy, the third one from military again, and so on. And topic assignments will vary with document. So that way, based on distribution of words and also topic mixture, you'll repeat that sequence until the document is full. That's the way LDA assumes we sort of come up with a document. Obviously, that's not the case, but because we operate here under the bags of words assumption, the order of the words doesn't matter. Also, the sort of context largely doesn't matter as well. So then the way it discovers those latent structures is by looking at words that co-occur together. Here, as I've mentioned, the key assumption is bag of words, that word order doesn't matter here. In terms of hyperparameters, again, the number of topics is important here. So I would iterate and try 5, 10, 15, 20, 25, 30, depending on, obviously, on the corpus you have. You can see the variations in terms of the topics you will have. Then there are two other hyperparameters called alpha and beta. Alpha is basically it controls the topic distribution at the document level. So if alpha is higher, documents tend to discuss many topics. and if beta controls the word distribution at the topic level. So if we have a higher beta, topics tend to include many different words. But rule of thumb is usually having alpha at 0.1 and beta at 0.05. Here, if we had to take my example, we can have 3 topics in the word coverage, like sanctions, and LDA will give me just the number of the most sort of common words there, right? So sanctions, economy, bank, oil, prohibition, dollar. I can assume that this this cluster of words mean sanctions. And then same goes with military and diplomacy. Obviously, a lot of it will, again, sort of to reiterate my point, would depend on your domain expertise as well as your knowledge of the documents you're analyzing. One of the key limitations of LDA, besides the fact that it ignores sort of context, is also that it ignores metadata. But a lot of questions that we want to answer in social science actually have to do with metadata. So we don't just want to understand a specific corpus, but we want to see how topics may be vary depending on the source that they come from, or depending on like the date that that source was when the document originated. And that's why we have structural topic model, which is basically a continuation of LDA in a way. It came out much later, and now it used to be popular a couple of years ago before sort of everyone moved to AI and LLMs. But it's still a useful tool that you can definitely use. It does, again, as I mentioned, it's similar to LDA, but it can help us understand the variation within the corpus. So in my specific case, maybe I wanted to understand if Russian media are more likely to focus on economic sanctions covering the war on Ukraine comparing to Western media. LDA sort of allows us, not LDA, STM is basically an LDA plus regression. And it allows us to sort of model topics as a function of metadata or the function of covariates that we have. It allows us to estimate 2 dependent variables, which are topic prevalence as well as topic content. In my case, I used here, you can see that I used 15 topics, and in terms of my topic prevalence, I wanted to understand sort of the slant, whether it was a Western or Russian slant, as well as number of days or when the article came out. And here's just my results. You can see after I labeled the topics, you can see that this is just the entire corpus with both Russian and Western media. You can clearly see here that diplomatic negotiation, Russian military gaze, and Western aid of Ukraine are the 3 main topics that both Russian and Western media sources have covered. On the other hand, Russian casualties and mobilization, sports and sanctions, and air raid alerts are 3 topics that weren't covered as much. But what the previous graph, so this graph I could have gotten with LDA as well, but what STM allows us to do more importantly, is sort of understand how, let's say, Russian versus Western media covered the war. So here we can clearly see, and on if the dot is on the right here, it means that Russian media covered this topic more. Here, Western aid to Ukraine, Ukrainian strikes on Donbass, Russian military gains, diplomatic negotiations, air raid alerts were covered much more by Russian state media. On the other hand, Russian casualties and mobilization, anti-war repression, Russian identity and culture, humanitarian crisis, sanctions on Russian economy, countering Russian influence, missile and drone attacks were covered much more by Western state-affiliated media. So it kind of allows us to see what, in terms of agenda setting, what topics were more important for different media sources. Similarly to LDA, both LDA and STM allow us to see top words for each topic and how likely we are to see them in each topic. The main and sort of researcher decision here is number of topics. Here you need to sort of balance between something called semantic coherence and all other metrics. So you'll have to sort of run the models with different number of topics, so from 5 to 30, let's say, and then plot all diagnostic metrics for each of those number of topics. Here you can see we basically what happens is we need to pick our topic at a point called elbow, where the adding more topics basically diminishes returns. Here, in terms of semantic coherence, we can see that it stays rather high, but here we can see it definitely sort of the decrease in terms of whether the topics are semantically coherent. And same here, same with lower bound, same with the residuals, holdout likelihood as well. We can see that it kind of plateaus around 20, 15. In my case, I chose 15 just because when I was reading the topics themselves, it just made more sense. But obviously, depending on your needs, you can change it as well. I will not talk about the meaning of each diagnostic metric, but if you want to stop at them, if you want me to stop and talk more about them during the Q&A, I'll be happy to do that. Well, the downsides of STM as with LDA includes the fact that it's a back of word approach again, and because there is this the researcher is the one choosing the topics and also interpreting the topics. There's definitely some sort of researcher degrees of freedom, which is fine because it happens either way, but you sort of need to be transparent about the choices that you make. Okay, so the last model that I wanted to talk about is something called Key ATM. This one is the sort of latest in terms of topic modeling. It's excuse me. Okay. The paper, the Key ATM paper came out in 2022, so not too far ago. What it basically allows us to do is to look for specific um, if, to look for specific topics, and it gives a researcher more freedom to determine what the topics are. Um, it's in this case, it's not really unsupervised topic model. It's more of a semi-supervised topic model because it does combine a small amount of information before that researcher gives it. So, for example, let's say you wanted to look for um, specifically for sanctions, for the information about sanctions on in on this large corpus about the war on Ukraine. You can include certain words in this in your topic, and a KATM will be able to sort of show how the topic varies between different sources as well as um, time, etc. So it's very useful when a researcher is interested in measuring a very specific topic. It's less exploratory compared to LDA and SDM, but it can be very useful if you, especially for hypothesis testing. I'm gonna skip this. But basically, yes, you provide a small set. In my case, it was Russian of Russian keywords for each topic you want to measure. Let's say you wanted to measure three topics like sanctions, military operations, and diplomacy, and the algorithm basically will track those words within the corpus. Here's the comparison between three of those models, as well as the citations if you want to explore more of it, more of those topics. I'm gonna pause again for questions if anyone has any questions. Okay. If not, we're gonna briefly cover sentiment analysis as well. So sentiment analysis basically allows us to understand the emotions, the feelings, the um, be feelings behind a certain text. It can be either in terms of valence, like positive, negative, neutral, but it can also measure specific emotions as well. So we usually have two approaches to do sentiment analysis. One of them is dictionary based. So here it's based on bags of words approach. So we count emotion words from sort of a pre-built lexicon. You can get off the shelf dictionaries that are available online, or you can build your own. Obviously, building your own would be more resource intensive, but it would be probably more precise. Um, you can also do AI, which probably would work better just because they're able to understand the context more. And especially, I would recommend using transformers for social media because a lot of the jargon and context and sarcasm and irony is something that dictionary based approach would not allow you to sort of analyze. The problem with that is AI is famously black box, so you don't really know what's going on. Here with dictionary, you can control it much more. So sentiment dictionaries have a list of words which are scored according to some emotions or opinion content of the words. It can be, as I have mentioned, broad sentiment, so valence, either positive or negative. It can be emotions if you're specifically interested in, let's say, whether Russian media was more angry when portraying the war. You can measure that as well. And you can assign even specific numbers to each of those emotions. There are a lot of sentiment dictionaries that are off the shelf. They include General Inquiry database. Luke is really popular. I used NRC for my dissertation, just to try it. NRC is great because it's available in many languages. The only problem is with NRC is that they when the researchers created the dictionary, they crowdsourced the word from English speakers, and then they translated it to other languages. The problem with that is the same words might not work for Russian in the same category as they work for English, let's say. So in this case, I would say having your own dictionary would probably be the best. And here, if you decide to create custom dictionaries, you can do it through manual generations. So that would probably the most resource intensive path, because you will need to sort of look through different other dictionaries. You can also brainstorm with other people, but definitely would take a lot of time to generate that list. You can also crowdsource it through other people. So you can do a large survey analysis as well, and where people assign their feelings about different words on a different scale. That would also require more financial resources as well, besides just time. And you can also do statistically, so try to identify different distinctive or separating words. In terms of how to use it, you can choose a relevant dictionary, match words in your text to that dictionary, and sort of then simply calculate the proportion. So it's pretty simple. So the emotion score would be just a summation of emotional words divided by the summation of a sum of total words. We have a pretty simple ratio here. Again, sort of the limitations of it is they don't understand the context. They often use sarcasm. They a lot of words have multiple meanings. So bank in English, for example, can mean can have multiple meanings. Well, the number 4 about the translation, I've mentioned that already as well, that some NRC words that were crowdsourced in English might not translate into Russian that perfectly. And then dictionary choice matters hugely. So you need to be really careful with what dictionary you would like to work. And if you do work with dictionary, maybe if you're doing more of an academic work, you will need to sort of use multiple dictionaries to make sure that your results are robust to different specifications, right? Okay, so the transformers work much better here because let's say here we have the sentence that sanctions don't work. Dictionary approach would miss that context, but transformers or AI would totally understand it. In terms of transformer-based sentiments, you can sort of send each article's text to the model through API or Python, and then model will return probabilities for each of the emotions, and those probabilities sum up to 1. You don't need any manual calculation, and then I analyzed my text with mixed effect regressions, same as with dictionary scores. For Russian sentiment analysis, I would probably use either Dostoevsky or this Zboev, Naumov, and Rybka approach. Both of them are pretty um, good in terms of classification. The problem is that Dostoevsky, for example, only works well for social media because it was trained on social media, but it might underperform on news text in my case. But if you do work with social media and you want to understand valence, just positive, negative, neutral, I would work with that model. If you want to understand specific emotions like joy, sadness, anger, fear, surprise, I would work with the second model. Here again, um, the the problem is like you need to know what the model was trained on. Here it included a mix, I think, of social media posts as well as some news. So that's why I used the second model as well, and for myself. Um, this is just tells you this graph just tells you the process, the downstream process that I went through to analyze to sort of do sentiment analysis on my data. Um, and here we can see that if I use, this is using AI, a transformer, here we can see that honestly, there is not a lot of difference between Western and Russian media when in terms of expressing different emotions and joy or sadness or fear or anger. So that was surprising in a way because we usually associate more authoritarian regimes with higher intensity of emotions. But here's we can see, I mean, there is some movement here for Russia, but it's not really statistically significant. Here we can see it divided by different sources, and not surprisingly, Channel One and RCID are scoring the most in terms of emotional intensity across all emotions, while Russia Today, RT, surprisingly scores much less than the other two Russian Russian state-affiliated media. So the six takeaways from today are sort of pre-processing. Uh, Pre-processing is important, and tracking and being transparent about those choices is necessary, especially if you are in academia. The second takeaway, that language and the structure of the language are important as well. So Russian morphology requires us to pre-process the text in a different way from English. The third one is that if you decide to do topic modeling, you need to understand what your question is. LDA is very useful for the exploration. STM if you want to incorporate metadata, and KTM if you have a specific topic. Both dictionary and transformers sentiment approaches, sentiment analysis approaches should be used. It just depends on your constraints, I would say, on how many resources you have. The fifth one is I did not mention it, so I'll just keep it. But number 6 is important. It's all about the validation. So computation is important, and having cool methods is important, but don't dismiss like qualitative reading and domain expertise. Tomorrow we'll be coding in R. I'll show you some of the code that I have that will cover both topic modeling and sentiment analysis. I'll stop here. Let me know if there are any questions.